irresistible force such as you meets an old immovable object like...
In this lesson, the essential question will be, is the function continuous? A graph that is smooth without any holes, jumps, or asymptotes is called continuous. Informally, that means you could draw a continuous graph without lifting your pencil from the paper. The more complicated a function becomes, the more complicated the graph becomes. A function can have holes in it, or it can jump, or it can have asymptotes, just to name a few variations. Now back to the question, is the function continuous? Or in other words, if not, then does it have a point of discontinuity? This is the function 1 over x squared. This is an example of an infinite discontinuity at x equals 0. Please note that this function is continuous when x is greater than 0 and when x is less than 0, but it is discontinuous for x equals 0. This function has a segmented definition. It's also called a piecewise function. That means it includes different expressions for different parts of its domain. It's also an example of a jump discontinuity. This is a graph of the function absolute value of 2x over x. This function's undefined at x equals 0, and this function has a jump discontinuity at x equals 0. This is another one of those functions that's a little deceptive looking. It looks like it's a nice, smooth, continuous function. But if we look at the table, at x equals -1, you can see there's a break. So this is an example of point discontinuity. So the last thing we have to discuss is these functions that aren't continuous at an x value. They either have a removable discontinuity, a hole, or a non-removable discontinuity, such as a jump or an asymptote. If the function factors and the bottom term cancels, the discontinuity is removable, so the graph has a hole in it. Let's take a look at an example. Stop the video now and determine whether or not a function g of x is continuous at x equals 5. So you can tell right away that 5 is going to be a problem in this function. If I look at the table and I go down to 5, you'll see when I insert 5 in to the function, it's undefined. A little bit of algebra on the actual function itself. If I plug 5 in for x, let's see, 5 squared, 2 times 5, minus 15. I think I'm going to get 25 minus 10. It's 15. Minus 15 is 0. So this function is going to be undefined, and the denominator is going to be equal to 0 if I try to determine a value of this function where x is equal to 5. Factoring the numerator and denominator, let's see, it looks like I'm going to get a common term of x minus 5, which will leave me with the function, the reduced version is going to be x plus 1 over x divided, x plus 1 over x plus 3. Now, 5 will work in this simplified expression, but you have to remember, this isn't the original given equation. The graph is going to look and act like x plus 1 over x plus 3. but the original function is still going to have a hole in the graph. Therefore, we say that g of x has a removable discontinuity at x equals 5. You can also see from the graph that this particular function has an infinite discontinuity at x equals a negative 3. And let's not forget the hole in the graph, the point discontinuity at x equals 5. So just to quickly review, we have seen examples of infinite discontinuity, jump discontinuity, and point discontinuity, which leads us to, when is a function increasing, decreasing, or constant? Let's take a look at the function x squared over x squared minus 1. For a function to be increasing on an interval, any line containing 2 points on the graph within the interval must have a positive slope. Please stop the video now and decide whether the function increases on the interval from negative infinity to 0. Let's look at this last problem. If I pick any 2 points in this interval from negative infinity to negative 1, I'm always going to have a positive slope. But now if I say from negative infinity to 0, let me pick 2 points, any 2 points I want. Here's one, here's another. You'll notice that this is going to be a downhill slope. So you can't say that this function's increasing from negative infinity to 0, although it seems to be going uphill the whole time. Keep in mind the same holds true for the other side of this graph. If I asked you when is this function decreasing, you'd like to say from 0 to positive infinity, but actually it'd be 2 intervals, from 0 to positive 1, and again from positive 1 to positive infinity. So, what can you do now? You can decide if a function is continuous. If it's not, you can decide if it has an infinite discontinuity, jump discontinuity, or point discontinuity. And you can decide when it's increasing, decreasing, or constant. That's the end of this lesson. Thank you for your time and attention.
As sure as we live, something really got